So we talked a lot about black holes, and we have a lot of questions about black holes. So extraterrestrial, I'm not too sure who extraterrestrial is, perhaps an extraterrestrial joining us from maybe Mars or Venus. But they've asked, if two galaxies collide, would a black hole from another galaxy be able to suck in something from that galaxy?
Yeah, that's definitely possible. So when black holes collide, if there's any stuff immediately around them, like the accretion disks, then they can bump into those accretion disks and eat the material that's in them. And one thing I didn't talk about is that time gets really weird when you fall into a black hole. So when you get close to a black hole, time actually starts to slow down for you from someone looking very far away. So all of the stuff that gets eaten onto a black hole be torn to pieces by its gravity and fall into the black hole. And it doesn't need to be material from another galaxy that falls into it. Sometimes black holes can tear apart stars that are just get too close to them. So there are things called tidal disruption events that we see where stars get torn to pieces and we see their big bright guts orbiting black holes very, very far away from us.
Yeah, and extraterrestrial also asks if the black hole would be so could there be a situation where a star is or a planet or something is larger than the black hole, and so the black hole just cannot suck it up as it moves past it or something like that?
Well, yeah, so you could have a black hole that's smaller than the sun, because black holes need to be quite small so that the gravitational pull can make the black hole pretty much. I'm not sure exactly what would happen if you just threw a black hole through the center of the sun and it comes out the other side. It would eat some stuff of the sun, probably disrupt it quite a bit, but it depends how long it's around the black hole for.
Yeah, I think that's spot on.
I think there was actually a new class of supernova that was suggested this last week, where you have a big star that's not ready to die yet, but something like a neutron star or a black hole just enters into the star and causes it to be unstable and it collapses or blows up on itself. So that's a very good question. It's one that is still being actively researched by astronomers around the world.
Yeah, so it's true that as the black hole gets more mass, it kind of evaporates, right?
How do you mean, sorry?
So it's just kind of evaporating slowly, the black holes, through kind of Hawking radiation kind of process.
Yeah, so the tricky thing there is, though, that they need to emit more stuff than they eat at any given moment. And some young stars might have heard of something called the cosmic microwave background radiation. So this is the radiation at the end of, well, if you're a Hereford building the universe, you would know all about it, since we covered that in great detail. But it turns out that it's all through space, and black holes will eat light from the beginning of the universe all the time. So they need to wait until they've eaten all of that light before they can properly disappear.
So Zara asks, can you tell us about spaghettification?
Yeah, that's a very good thing, a very interesting thing as well. So spaghettification is what happens to you when you fall into a black hole. So it's so on Earth, let me say it this way. So we talked about how the force of gravity depends a lot on distance. So the sun has a weaker gravitational pull on the moon than what the Earth does. So the moon goes around the Earth, or at least from our perspective. But the same is true that the gravitational pull on your head from the Earth is slightly less than the gravitational pull on your feet. And it doesn't matter so much on the Earth, but if you're falling into a very massive object like a black hole, then the gravitational pull on your feet is a lot stronger than the gravitational pull on your head. So your feet get pulled in much faster than what your head does. So then the term to describe this process of you getting stretched out is called spaghettification, as your feet accelerate faster and faster into the black hole and your head gets kind of left behind. until you end up with a point where each of your atoms will be kind of stripped away from each other, and you'll end up as just an accretion disk around the black hole. Another question is, would it be painful to be spaghettified? I don't know.
Would you rather go in head first or feet first?
Well, if you went feet first, you might feel what it's like. I know that might be interesting. It might be painful. Who knows? What about you, James?
I think head first. I think I think maybe that will be a better way to become spaghettified. Okay, so here's a question for you by extraterrestrial. It's more about gravity than black holes, but black holes are involved. Actually, yes, yeah. So if we suddenly took our sun and we swapped it for a black hole of the same amount of mass, so we just swapped out the sun for a black hole with the same amount of mass, would the planets continue to orbit, or would they all be sucked into it?
That's a very good question. And it's a question I actually make videos every now and then for YouTube. And I made this a video on this topic, which you might want to look up afterwards.
Some
but
people in the chat are thinking sucked in. Some people are thinking it would be the same. Maybe we just get a 30-second poll. Who thinks it'll be the same?
Let us know if you think it's sucked in or not.
People asking when it stops orbiting. So orbits are just, the whole solar system is just orbiting like it normally is, and we just grab the sun and we replace it with a black hole of the same mass. It means it'll be much smaller in size, in radius, but it'll be equivalent amount of mass there.
So remember, what did we talk about before? Gravity only cares about two things. If we've changed the sun with a black hole with the same mass, does gravity care? What were the two things that gravity cared about?
Reggie says neither of those options. Ooh, maybe Reggie has some ideas.
Distance and mass, yeah. So if you've not changed the distances and you've not changed the mass, have you changed anything at all as far as gravity cares?
That's right. It's probably going to stay the same. I mean, there's going to be one obvious thing that will change. It's about light. We'll have just nights forever on Earth, which won't be good. I think all the planets might die. I don't think they'll have anything to photosynthesize. And that won't be good. But apart from that, I think the orbits will stay the same. All the planets will be doing exactly what they're always doing.
There might be some small effects, some tidal effects between Mercury and the surface of the sun, but anything past Mercury, I don't think would care. Even Mercury probably wouldn't care too much. So the planets would just keep orbiting if you just swapped one for the other in an instant.
Oh, so there's a very nice question from, I think it's Devi's here. So could a black hole eat an entire galaxy? So what's kind of preventing black holes just eating the entire galaxy? You just showed us some supermassive black holes that are in the center of galaxies. Why aren't they eating everything?
Yeah. That's a very good question. So it comes down to something called angular momentum. Have people heard about that before? Let us know in the chat. Have you heard of something called angular momentum? Some people talking about spaghetti there. That makes sense. No, a lot of people haven't. Okay, nope, so angular momentum is something to do with when you're spinning. So if you've gone on like a merry-go-round or something where you go around something, if you keep going around something with a very constant speed, then you have a constant angular momentum. Now, if you try and go towards the center of that spinning thing, it's kind of tricky, and you need to apply a force. You need to make yourself move toward the center. And likewise, if you want to move away, you need to, well, that gets complicated. You can be thrown off, but that doesn't matter so much. You need to apply a force to get closer to the center. So this angular momentum is kind of stopping everything from just collapsing down into a point, because the smaller it gets, the faster it spins. And this is why we make accretion disks. It all kind of collapses down into a nice disk. But with the galaxy, you can imagine at the beginning of the universe, when galaxies were forming, you had enormous clouds of gas and dust in space, and they were slowly condensing and collapsing down into galaxies. You had stuff from very far away coming much closer, and it has lots of this angular momentum, so it can't really move into the black hole too easily. So it takes a very long time. It may be true that in the far distant future, black holes will have eaten everything that can be eaten, but that will take an incredibly long amount of time.
Yeah, and gravity is very weak. I mean, we've talked about how weak it is too. So it's not like, you know, the black hole is talking to the furthest corner of the galaxy and trying to pull it really strongly towards it. It's very weak. It goes off with the distance you are away from the black hole. But, you know, all these things are kind of, you know, spinning things like to keep spinning. I think that's the deal with angular momentum. Spinning things like to keep spinning. Everything's kind of spinning around the galaxy, spinning around, and it kind of just wants to stay there. It would just keep spinning and spinning if there wasn't any kind of frictional losses. So I think Ryan is right on topic there, saying that, yeah, all these things are spinning. Gravity's so weak. It's not, everything's not going to be eaten by the black hole unless maybe you grab the black hole, try and move it all around and do all kind of crazy stuff.
I wonder how you grab a black hole.
Yeah.
I see one. It's kind of funny. Bob asked, like, can you have a black hole noodle? Can you change its shape? And that's actually a really pretty big physics question, because when you have two black holes that are colliding with each other, they're warping space, and they'll probably be warping their own surfaces. And exactly how the surfaces of the black holes change is also a very hard problem to understand. How do they actually connect with each other? So, although you might not be able to get black hole spaghettis, you might understanding how black holes pull on other black holes is a really hard problem.
Yeah, and Charlotte actually asked that. She asked, are black holes the most spherical objects in the universe?
It's a very good question.
I think we have to distinguish here, though, quickly, like the event horizon versus the black hole. Like the black hole is kind of a singularity. It's kind of just that the space has just gone into a singularity. You know, there's kind of just infinite curvature of space. It's all your trampoline. You've pulled the trampoline mat all the way down into a single point somehow. Yeah, and then so can you still hear me, Ryan?
Yeah, sorry, I dropped out for a bit there.
Oh, no, I think I may have dropped out. So the event horizon is the thing where, you know, once you cross the event horizon, no longer can you speak to anything outside. And that's the thing that's kind of more spherical. Like the black hole is like a point inside. I don't know. It's really funky stuff, right? It's funky.
Yeah, it doesn't really make much sense. Like time reverses and kind of becomes like space when you go inside of a black hole as well. So that doesn't, or go past the event horizon. So it's not easy to understand for any of us. I still don't understand really what's going on. But the sphericalness of them, I think you can warp the event horizon. I think it's called an ergosphere. So black holes can spin. And I think the ergosphere, let me quickly Google, is the ergosphere is the kind of the rotated event horizon. So it's like with spinning stars and things, they'll kind of squish. And if you spin a black hole fast enough, it'll also kind of squish. But you need to spin it in awfully high speeds for it to squish, and it probably won't squish too much.
Yeah, so that's an excellent answer to Stephen Felix's question. Do black holes spin on their axes? I mean, yes, they do. They do. And if so, is their equator wider than their poles? So I think Ryan just kind of answered.
Yeah, those are both true.
So a black hole is a 3D object. That's correct, Stephen Felix. They ask if it's 3D. Yes, it is 3D. It's kind of hard because, you know, when we talk about trampolines and warping space on trampoline, I mean, that's a 2D trampoline, but space is 3-dimensional in space. And when you warp it, you kind of have to think about kind of scrunching up a 3D thing or something like that. Like, it's a bit weird. So we have many other questions. I think you've answered this one. It's also associated with angular momentum by extraterrestrial again. What makes Saturn's rings stay in the kind of ring-like shape? You know, why aren't they kind of uniformly spread all
Yeah,
around Saturn like a shield?
yeah, it's a very good question. So it comes, angular momentum is the reason for a lot of things that happen in the universe. So disks and disks and kind of balls are very common in the universe. So gravity wants to pull things together, so it'll pull it into a ball, but angular momentum wants everything to be in a nice disk at the same kind of distance away that it wants to be and just going around something. For Saturn's rings, it's a bit more complicated. So that probably would have been formed by one of Saturn's moons being torn to pieces. And it's being maintained by little moons inside of the disk, going around it, tagging on the disk so that it stays in a nice ordered shape. So Saturn's rings are a little bit different from accretion disks, but overall, it's the same kind of principle.
So maybe we'll have one more question because I see it's getting a bit late now. But people have been asking about white holes. So, you know, we've talked about black holes. What's on the opposite side of the spectrum? Maybe it's a white hole. Sophie asked, could white holes exist? And if so, what could they be? And Daniel has just asked also, do white holes exist?
Yeah, both very good questions and very interesting things to consider. So, as James said, a white hole is like the opposite to a black hole. So if things fall into black holes and never come out, then a white hole would be something that is just making stuff. So the name is kind of appropriate because black holes, we can't see anything about them because they just suck in all light. They're just a void in space pretty much. But a white hole would be emitting an awful lot of energy. And you'd see it kind of as a blinding flash of light. We haven't seen any white holes in the universe so far, but the research I do is look for exploding things, usually things like supernova. So what we do for that is we just look at the sky very often and see if something has changed in the sky. And what you could do is if you see that something has exploded or something new has appeared that's nowhere near a galaxy or nowhere near something that could have blown up and doesn't look like anything that we know of how they blow up, then it could be a white hole. But so far we haven't had any observations for white holes. And if we did find them, that would be pretty amazing because so far, as we know, there's no way to make new matter in the universe. Whereas a white hole would kind of just be periodic ways the universe could fill itself up with more stuff every now and then without needing a new Big Bang.
Yeah, really cool stuff. And, you know, these are very big fundamental questions that the young stars have stumbled into within 30 minutes of having an event. So this is just some awesome questions from the young stars. Lots and lots of curiosity out there.